Hello everyone, I'm Nigam. So I'll be talking about a recent work of ours, which is titled as Phases and Phase Transitions in a Dimerized Spin-half XXZ chain. So this work is done in collaboration with Ashirvad and Tapan from NISAR, Diptiman from IIC, and Shubhru from here at ICT. So before starting, let me give a little motivation for studying quantum spin chains, which have recently attracted renewed attention in the context of classification of symmetry-protected topological phases, and more recently in the context of non-invertible symmetries. And these quantum spin chains are also an ideal platform to check the ideas related to unconventional quantum phase transitions, which lie beyond the symmetry breaking paradigm of Landau's. Uh, in this particular work, I'll be talking about a spin half XXZ chain. I'll tell what that is. And there exist various versions of them. And these are the minimal model to explore the ideas related to unconventional quantum phase transition. And there is a parallel development in the field of experiments also. Like people can simulate these spin chains using ultra cold atoms and Rydberg atom arrays. So this is the model that we have studied. So this is a simple XXZ model. XX, we are calling it because the XX plus YY form has uniform coupling, and dimerized because this GG part is dimerized. I mean that for even and odd bonds, this coupling alternates between JB and JA. So this is written in spin half language. These are polymatrices only, and one can do Jordan-Wigner transformation to write it in language of spinless fermions. So in this language, it turns out to be a free fermion hopping plus this density-density interaction on nearest neighbor sides. But now this density-density interaction is dimerized because of SG being dimerized in the spin language. So now as a disclaimer, let me show this phase diagram that we have and the related phases and associated phase transitions. Then I'll try to explain why we are getting there. So we have made the phase diagram in this JB-JA plane for a fixed value of J pers, which we have fixed to 1. So this 45-degree line where JB is equal to J is the normal undimerized XXZ chain. And that is very well studied. So up to Heisenberg point is the point where JB and J both are 1. We have a gapless Luttinger liquid phase. And beyond that, we have a Ising-Neal gapped phase. So pictorially, these are represented like this. So Ising-Neal is like alternatively filled and empty sites, which is like antiferromagnetic ordering. But as soon as we turn on the dimerization, we get 2 more gapped phases, which we call Ising paramagnets. And these subscripts 0 and pi denote their Berry phases. So this Ising paramagnet is trivial, while this one is topological. And the phase transition between these two is a topological phase transition, while phase transition between IPM pi to IN lies in Ising's university class. So to understand this Ising class, this transition lying in Ising class, we can start from extreme limit. Let's say, so let me tell you that this critical line will curve and will touch this JA axis at infinity. Similarly, this line will touch JB at infinity. So let me start from an extreme limit when either JB or JA are very large, and then we turn on other part of the Hamiltonian as perturbation, and then see what happens. So let's start with this limit when JB is very large, let's say infinity. So when in the JB goes to infinity limit, this is the dominant part of the Hamiltonian. So let's take JBs are defined on these blue bonds. So let's take one bond. So ground state for a single bond will be this thing, up down or down up. Let's call them plus and minus. And now we define these new. So remember these S spins were living on these sides. Now we define these sigma spins which live on the bonds, these blue bonds, center of blue bonds. And we turn on J and J perp as the perturbation, and we do strong coupling expansion or degenerate perturbation theory. And we get this quantum Ising model as the effective Hamiltonian in this JB goes to infinity limit. So since this is a quantum Ising model, which in one dimension, it is exactly solvable. We know the transition from a ferromagnet to paramagnet lies in Ising's university class. So this explains this transition from IPM 0 or IPM pi to lie in Ising class. So we started with JB goes to infinity limit. We can start from other limit also, like J goes to infinity limit. We'll again get a quantum Ising model, but now these sigma spins will be defined on the center of these blue bonds. But so at the level of effective Hamiltonian, it looks same. But this is little different because when J is very large, then these two end sides will be decoupled from the rest of the chain. So there will be spin half lying on these decoupled sides, which will have a degeneracy of 4. And this degeneracy will be like edge modes. and it will be protected by time reversal symmetry. So it is a topological phase. So it explains this part of the phase diagram, that we have a topological phase on this side and a trivial phase on that side. Uh, okay. Now let me show the numerical calculations which were done using DMRG. So we calculated von Neumann entanglement entropy, which is related to central charge in one dimension through this Cardy-Calabrese formula. So we calculated this and we did the curve fitting to obtain the value of C, and that is plotted in this JBJ plane. So for every gapped phase, value of C is 0, and along this 45-degree line up to critical point, we have value of central charge 1. And at at this Heisenberg point, this C equal to 1 line becomes unstable and it breaks into two C equal to half lines, these two. So this is the understanding at the level of central charge. So to match these numerical results with the calculated analytical results, we calculated the charge gap as we go from IPM pi to or IPM 0 phase. So this is the charge gap, we obtained it numerically. And to check its matching with analytical results or not, we calculated the coefficient, this coefficient nu through Bosonization calculation. I'll tell about what that is. And then we try to do the finite size scaling with the known, with the analytically calculated exponent. And we see these numerical results collapses very well with the analytical exponent. So the numerics and analytics are both in accordance with each other. Now let me talk about bosonization. So I'll say a few words like it is a mathematical technique to map an interacting fermionic theory in 1+1 dimension to a massless non-interacting bosonic theory. So the idea behind bosonization is that in one dimension, so these plots are for one dimension and these for 2D and will be true at a qualitative level for higher dimension. So in one dimension, we have only two Fermi points. Let's call them left Fermi point and right Fermi points. And we have particle hole excitations. And this is the particle hole excitation plot. So near the Fermi points, we have a linear spectrum in one dimension. So the particle hole pair, which are bosonic in nature, form a coherently moving pair in one dimension. While in high dimension, they can't do that because of this continuum which exists everywhere. So that was the physical motivation for bosonization. Now, don't look at the all equation, but this is the, so let's say psi is the fermionic variable, which is defined near the Fermi points, either left Fermi point and right Fermi point. And that can be written in terms of bosonic variable phi and theta. So this is the mapping between fermion to boson. And this phi and derivative of theta follow these commutation relation. So phi and derivative of theta are like canonically conjugate variable. So we do this transformation on the original spin Hamiltonian or fermionic Hamiltonian, and we get this bosonized form. So this is for the 45-degree line, very well-known XXZ model, not dimerized. This is the undimerized limit. So here we have a quadratic part, which is a harmonic part, and here we have a cosine 4 phi kind of potential. And this lambda is proportional to strength of SG interaction, and this K is some non-trivial function of parameters of original model. So this is in literature, it is known as Sine-Gordon model, and it is very well studied. So the phase diagram for normal XXZ chain looks like this. So if we plot it as a function of lambda, below lambda for lambda less than 1, we have a gapless Luttinger liquid phase. Beyond that, we have a Ising-Neal phase. So, and how is this line defined in the K language? We can see by calculating these SG or S plus S minus correlation functions. So these are the correlation functions. And let's see, we get this K variable here. So if K is less than half, then this term will be dominant. So SG will go like proportional to -1 to the power x. So it will be like Ising-Neal kind of ordering. So it will be a quasi-long range order. But when this term is, when K is lying between 1 and half, then this part will be dominant and we'll have a gapless Luttinger liquid phase. And for the critical point, we need these two correlation functions to match with each other. And that will happen exactly at K equal to half. When K is half, these two will look like same. At least the variable dependent part, X dependent part will look same. So K equal to half is the transition point. So in lambda language, it is 1, and in K language, this is half. Now we do the same bosonization for our model also. We get one extra term. So apart from cosine 4 phi, as soon as we turn on dimerization, we get sine 2 phi. So here delta is proportional to JB minus JA. So if JB is equal to JA, this term will vanish. And this lambda is proportional to JB plus JA. So this is the model. It is called as double frequency sine-Gordon model. And the beta functions for the couplings delta, lambda, and k can be calculated, and it looks like this. No need to focus on these equations, but we can plot them as a RG flow diagram, and it looks like this. So we divide the RG flow diagram in two parts. Remember k equal to half is the critical point. We divide it in k greater than half part and k less than half part. So for k greater than half, we see that this lambda becomes irrelevant as soon as this coupling flows towards lambda goes to 0, and we go to the finite value of lambda, which is either positive or negative. And depending on the sign of delta, we get Ising paramagnetic trivial phase or Ising paramagnetic topological phase. But for k less than half, this is the origin. Remember, delta is proportional to JB minus JA, and lambda is proportional to JB plus JA. So origin is the point where JB and JA both are 0. So this is the C equal to 1 point. And we see that there is a flow to, there are two new fixed points, which are Ising fixed points. So there is a flow from a C equal to 1 fixed point to two C equal to half fixed points. So this explains that why this C equal to 1 line becomes stable and breaks into two C equal to half lines. And this is in accordance with Jamalochikov's theorem, which says that in RG flow diagram, flow is always from a fixed point with higher central charge to a fixed point with lower central charge. So we can linearize our beta functions about this critical point, which was k equal to half. So we do this k equal to half minus epsilon expansion, and we linearize our beta functions, and we get this equation. So one can solve this to obtain this form for delta and lambda. This is the relation between delta and lambda at the critical point k equal to half. You can see this epsilon comes in the denominator of the exponent here. So if we go in epsilon goes to 0 limit, then this delta depends on lambda tilde in a singular way. So if you remember the phase diagram, which looks something like this, this was C equal to 1 line, it breaks into two C equal to half lines. But this opening is in a very narrow way. So it is opening, it is not just going like this. It is opening in a very narrow way, and that is explained by this equation. So if we remember delta is proportional to JB minus J and lambda is proportional to JB plus J. So if we plot this in JB-J plane, it will explain this narrow opening. Okay, so all these things can be done. So we found a duality transformation for our dimerized XXZ model, which is dual to some form of dimerized quantum Eschken-Teller model. So everything can be that I talked about can be studied from by starting with this quantum Eschken-Teller model. So let me say a few words about this duality transformation. So this is the dimerized XXZ model, which we have written in a dimerized way. Here mu are the Pauli matrices. So now we do some rotation, and we do some Kramer's vernier, which I'm not talking about here. So remember, these mu spins are living on these sides, black sides. But after doing Kramer's vernier, we get two new spins, which we call tau and sigma. And this tau and sigma lives on the center of these blue bonds. So after doing all those duality transformation, we'll get this Hamiltonian, which is dual to our model. So here we have tau and sigma, which live on these sides. So quantum Eschken-Teller is nothing but the two copies of quantum Ising model. See, this is the ferro part, this is the transverse field part. Similarly for this, and these are the interaction between. So it is like two copies of interacting quantum Ising models. So along this 45-degree line, we have two quantum Ising model. So central charge will be half plus half. For one quantum Ising model, it is half. And since there are two, so it will be half plus half, so 1 for 45-degree line. But at this critical point, these two quantum Ising models become non-interacting, and they drift apart in opposite direction, like this one. So we get a single copy of quantum Ising model here, a single copy here. That's why one copy half. So everything can be studied from this model, like all the symmetry protected topological phases and phase transition can be studied starting from here. And details about that are in this reference.
Thank you, Harsh, for the interesting talk. Do you have any questions?
Yeah, so in the second plot, you showed about the topological unit in which we are. Yeah, so can I expect any different dynamics here or any transport properties specifically in the topological limit?
Topological limit, if you mean this edge, so if you have open chain, then you'll have these zero energy modes lying on the boundary. That will lead to different thing at the boundary in terms of transport, but in the bulk it will be same as the trivial part.
You mentioned that in the first few slides that this XXZ chain can be used to study this unconventional quantum phase transition. So what do you mean by that unconventional here?
So, I meant specifically this phase transition from IPM0 to IPM5, which is topological phase transition. There is no symmetry breaking on the either side. So it is beyond the Landau's symmetry breaking theory.
You basically mean the topological phase transition
Yeah.
kind of stuff.
There are no more questions. Thank you, Harsh, once again.